Okay, so this is question 3 from the homework. It's describing a scenario where there's a 240-gram ball colliding with a wall. So it's asking us what is the final velocity of the ball. In order to solve this, we have to make the assumption that the ball's momentum is changing over time due to a force being applied to it. And this is a valid assumption, seeing that there is a force being applied to it according to this graph. And velocity is changing, which means that there must be momentum on the ball. So okay, knowing this, we can apply Newton's second law to it, to this situation. So Newton's second law is basically just saying that force is equal to the change in momentum over the change in time. We can also rewrite this as change in momentum is equal to mass times the change in velocity, and we can put change in time there as well. And we can rewrite that as impulse divided by change in time. These are all the assumptions that come with this scenario. So from what I can see, we can get impulse from this force time graph because we know that the area under a force time curve is equal to the object's impulse. So that's an important variable. And we also know that the final velocity is going to be in this variable here. So I'm going to rewrite this equation. Basically just take this here. Vf minus Vi is equal to the impulse. This is where we can solve for Vf. Let's do that real quick. So Vf minus Vi equals impulse divided by mass plus Vi. We get Vf equals impulse divided by mass plus initial velocity. So we have our equation. Now all we need is to solve for our variables. We have mass, we are given mass, which is 0.24 grams, 0.24 kilograms. We get that from converting from grams to kilograms, which is just 240 divided by 1,000. Oops. And then we also have our initial velocity, which is negative 10 meters per second. Oops. that's given here. At time 0, the ball is going negative 10 meters per second, which is just the opposite direction. Then now all we need is impulse, and we can get that from this curve here. So to solve for that, it's an easy rectangle, so we'll just do our impulse is equal to the height times the width of this rectangle, so 500 newtons times 8 milliseconds, sorry. I'm going to convert the milliseconds to seconds here. So we just divide it by 1,000 because there's 1,000 milliseconds per every second. It's a quick, easy conversion. If we put that in the calculator, we get that impulse is equal to 4 newton seconds. We also know that this is equivalent to 4 kilograms times meters per second. And from here, we have all of our needed variables to solve for final velocity. So VF, we can plug it all in. VF is equal to the impulse, 4 kilograms times meters per second. Since all the other variables are in kilograms and meters per second, that's what I'm sticking to here, so that units cancel out correctly. Divided by 0.24 kilograms plus negative 10 meters per second. So if we put this all in the calculator, we get that final velocity is equal to 4 divided by 0.24 minus 10. That's 6.67 meters per second. Checks out, the units check out, and this is our answer. This makes sense, seeing that it's somewhat reasonable distance. You can round it up to 10. Just by looking at this graph, you can assume that it's somewhere near 10. It would be somewhere near 10. So I would say that this checks out.